Hello again. From today's lecture onward, we'll continue with graphs, but we will begin to look at not only control flow, I'll also discuss about modeling data and how to write test cases and define test paths that deal with handling about how data flows. Just to recap where we are in the course, we are looking at test case generation algorithms and test requirement definitions based on graph coverage criteria. In the previous week, we saw structural graph coverage criteria, which just were coverage criteria based on the structure of the graph, vertices, edges, paths, and so on. This week, I'll begin with dealing with the second part, which is data flow coverage criteria. And then after we do these two, very soon, we will look at various software artifacts, code, design, requirements, see how to model them as graph, and recap all these structural coverage criteria and data coverage criteria that we saw, and see how to use them to actually test these software artifacts. So the focus of today's lecture, and for a couple of lectures more to go, would be related to data flow coverage criteria. What we will be seeing today is what is data, right, in a software artifact, mainly programs as far as this lecture is concerned, and how to model data in graphs. In the next module, I will tell you about, once we have models augmented with data, how to define coverage criteria and what is the state of the art when it comes to defining test paths that achieve these coverage criteria. So, what is data? As far as programs are concerned, as far as many software artifacts are concerned, there's only one kind of data available. Data is available as variables. Variables could have types, variables could have simple types, variables could be complex types like arrays, several other user defined types, and so on. But whatever it is, all the data that a typical program deals with is basically represented as variables. What are these variables used for in the program? They are used because they represent some kind of information or data. And there are basically two kinds of basic ways in which we subject variables to the program, right? One is to say that a variable gets created at some point in the program, typically when it's declared and initialized, and at some point later in the program, a variable gets used. So it could be the case that certain declarations get missed or certain uses get missed. Suppose a variable that is not declared suddenly gets used in a program, then obviously the program will not compile. It will be a compiler error. Compiler will say that there is a variable that's not been declared in the program. But think of the other way around, right? A variable is declared in the program but never used at all. Maybe the program was large and this programmer meant to use this variable, so he declared it, but didn't really use it because it was wrongly declared. We really don't want such things to happen, right? So we want to be able to track a variable from the place where it is defined to all the places where it is used. And we want to check whether it is used at all or not. So what we will deal with throughout this lecture would be how to define data places where variables are used and what are the places where they are actually put to use, right? And then in the next lecture, we'll look at coverage criteria that will track the definition of a variable with reference to its use. So what is the definition of a variable? A definition of a variable is a location in the program where the value of the variable is stored into memory. That location could be an input statement, right? It could be an assignment statement. It could be parameter passing from one procedure to another. It could be any kind of statement. We'll call statements abstractly as locations so that we can smoothly switch between using statement as a location. And when we look at graphs, nodes for us will become location. Just to recap, what is definition of a variable? We use the word def for short. It's any location in the program where a variable is stored into memory. Its value is stored into memory. Assignment statements, input statements, parameter passing, procedure calls through parameter passing, all these could be places where a variable's value is defined. Now, a defined variable has to be put to use. So what is a use? A use is a location in a program where a variable's value that is stored is accessed by the statement of a program, by an assignment statement wherein it could be assigned to another variable. It is accessed because it is being checked as a part of a condition that comes along with an if statement, or it's checked, it's used as a part of a condition that comes along with a loop like for loop or while loop. So whenever a value of a variable is accessed, you say that that's a use corresponding to a variable. So a variable is defined and then in one or more ways, and then a variable is used in one or more ways. And typically, a program carries value of each variable from its definition to its use, right? So these pairs of definitions and uses of a variable are what are known as DU pairs or def use pair. So what is a DU pair? A DU pair is a pair of locations, say Li, Lj, such that a particular variable v is defined at Li and used at Lj. Please note that even though I have not mentioned here, v is an explicit parameter to a DU pair. Per variable, there could be several DU pairs, right? Per pair of location, there could be several variables that are defined and used. At any point of time, given a variable, you're looking at what its DU pair, and given a pair of location, you're looking at all the set of variables that are involved in that location, definition and use of that location. We may or may not mention it explicitly in this lecture, but there is always a parameter or an attribute to every definition or a use or a DU pair, which is always a variable. Because if variables are not there, what do we define and what do we use, right? So what did we learn till now? We learned what a definition of a variable is. It's basically a place where a variable's value is first time written into memory. Could be an input statement, could be a declaration, could be an initialization, could be parameter passing, several things. What is a use? A use of a variable is a statement or a location where a value of the variable is accessed. Its use could be because it comes on the right hand side of an assignment statement, or it's used as a part of a predicate that comes for checking for an if or for a loop condition. What is a DU pair? A DU pair is a pair of locations Li, Lj, such that the variable is defined at Li and used at Lj. So consider a program that is, let's say, modeled as a graph. We will look at graph data flow testing with reference to graphs in this module. So we consider a program that's modeled as a graph, and let V be the set of variables that are associated in the program, right? I want to know how these variables now come inside this graph, right? So what I do is I take the graph has nodes and edges, and per node and per edge, wherever it is applicable, I'll say which are the variables that are defined in that node, call as def of n for a node n, and for an edge e, I'll say which are the variables that are defined in the edge e, right? Typically, graphs that correspond to programs will not have definitions on edges. Will not have definitions on edges. As I told you, when is a definition? A definition is when a variable is written into memory. So it's like having an assignment statement as a part of an edge. It's rare it's rare or almost impossible in a graph that models a program. But for graphs that come as design models, let's say graphs that come as finite state machines modeling designs, it is possible to have definitions on edges. Definitions could be thought of as actions that change the value of a variable or side effects related to an edge, right? The subset of the set of variables that each node or edge uses is called use of n or use of v. So per node and per edge in the graph, we talk about what are the subsets of variables that it defines and what are the subsets of variables that it uses. So here is a small example. Here is a graph that has 7 nodes. Initial node is 1, final node is 7. Not all nodes have defs and uses, only few nodes have. What I have done here, I said at the node 1, there is a statement which says x is equal to 42. At node 5, there is another statement which says z is equal to x into 2. At node 6, there's another statement which says z is equal to x minus 5. So you can think of this statement x is equal to 42 that comes at the initial node 1 as defining the value of x at node 1, right? So we say definition 1, def of 1 is this singleton set x, right? 2 and 3 and 4, nothing happens. I move on, I look at 5. For statements at nodes 5 and 6 have expressions that calculate the value of z based on the value of x, right? So at 5 we have z is equal to x into 2. At 6 we have z is equal to x into 5. So these two nodes can be thought of as having statements that define z. So we say definition of 5 and definition of 6 both are the singleton set z, right? Now, how is Z defined at nodes 5 and 6? Z is defined using an expression that involves a constant and it involves the variable x. Similarly, here Z is defined using another expression which involves this constant 5 and a variable x. So we say the x is used at nodes 5 and 6. So is it clear? So the first occurrence where the value of x is initialized or set to some value or declared or read from input is its definition. In this case, the x is defined at node 1. And whenever there is a statement that puts this defined value into use, right, like here at nodes 5 and 6, we say x is used in those places. In addition to that, at nodes 5 and 6, the value z is assigned an expression involving x, and so we say x is defined at nodes 5 and 6. We'll look at a more detailed example to understand this clearly. So here is an example that deals with a Java code corresponding to a pattern matching example. Some version of pattern matching or the other, if you look at, you'll find it in several papers and books related to testing. It's one of the popular examples that we always deal with in testing mainly because it has got a lot of rich control flow structure. So what I have done here is I have put a Java code for pattern matching that was taken from this textbook, Introduction to Software Testing by Ammar and Ofut. What I've done is to make it readable, I've spread across this Java code over 3 slides. So we'll first go through the program line by line. We'll understand what this program does. Then we'll go ahead and draw the control flow graph of this program and look at how the data or the variables that come in this program can decorate the control flow graph. Where is it defined? Where is it used? Right? We'll use this example to understand the defs and uses of all the variables on the control flow graph corresponding to this code. Right? So this is probably the first full piece of code that you're looking at, and we will reuse this example at a few other places as we go down in our lectures. So what does this code do? This code takes 2 arguments, a subject and a pattern. Both of them are strings, and then it searches for a pattern in that subject, right? Like for example, I could say subject is a string which says institute. Pattern could be something like ins, right? If ins as a pattern comes in the subject, then you say that this pattern is found in the subject and you return the index at which this pattern begins in the subject. If the pattern is not found in the subject, then you return a string called -1. So that's what it says. So it says that you return -1. If the code returns -1, then you output saying pattern is not a substring of the subject. If the code returns any other character, then you say pattern does occur in the subject as a substring and it begins at this particular index. Yeah, one more thing to note is this: we look at a pattern as a contiguous substring. We don't look at it as bits and pieces, right? So this is the first slide containing the first half of the code, which does all the initializations and the main prints. The actual code is given and continued across 2 more slides. So here is the code that is continued from the first slide into the second slide. So as I told you, what is the goal of this code is to find the index of the pattern if it occurs in the subject, and it will return the index 0 based in the sense that we count indices as starting from 0. The first character of subject, this index is 0, right? If the first occurrence of pattern in the subject, we return -1 if it's not found. If subject or pattern is empty, then we throw a null pointer exception. Right? How does this pattern index work? As I told you, it takes 2 arguments, a subject and a pattern, and it does all these kinds of initialization. So it uses these variables not found. It initializes it to -1. It's an integer variable. It uses 2 other integer variables. I sub, you can read it as index that moves across the subject. It initializes the index of the subject to 0. And then it sets the return index to be -1, which is not found. Remember, when the return index continues to be -1, if you go back to the previous slide, I return saying pattern is not a substring of the subject. And then it uses a few Boolean variables, standing for is pattern, initializes it to false. and then it calculates the length of the subject and the length of the pattern. Why do we need the length of the subject and length of the pattern? Because we're going to use a for loop to move across the length of the subject from left to right, and another for loop to move across the length of the pattern from left to right. So here is the main part of the code. There is a while loop. Inside this, there is a condition, there is a for loop, and then there is an if loop. Why am I talking about this while, if, for, if? Is to tell you that this code has very rich control flow structure. The control flow graph of this code will involve some amount of branching, which makes it a very interesting case for testing. And here there are lots of nested loops, one inside the other. So the control flow structure becomes even richer. And so it's an interesting example to look at for testing. Now going back and understanding what the code is. So it says as long as is pattern turns out to be false, and pattern index is within the subject of the length of the pattern is within the subject index, then what do I do in this if loop? I start matching character by character. So I say wherever I am in the subject, which is this index of subject I sub, does it match the first character of the pattern? First character of the pattern is present at index 0. If it is, then you say that the return index could be this value. Let's say if you take the earlier example that we had, right? Let's say a subject was the string institute and the pattern was INS. So right up front at the index 0 itself, the subject and the pattern match, I and I match, right? So you set the index where it matches to be the return index, and then you set this Boolean flag, is pattern found, which is pat, to be true. Right now, what you do, you enter a for loop, keep incrementing the position that you look at in the pattern as long as you go till the end of the pattern, and see if every character of the pattern, one at a time, matches the corresponding character in the subject. That's what this if statement does. If there is a mismatch at some point in time, it says resets the return index to not found and makes is pattern false and comes out of the for loop. Right? If every character of the pattern continues to match the subject, it keeps incrementing the index in the subject, successfully finishes the for loop, and it will return this value here that it's set as the return index here. So is it clear what the code does? So just to quickly recap, we're looking at this pattern matching code. It takes two arguments, a subject and a pattern, and it uses a few Boolean variables to search for the pattern in the subject. What it does is initially it assumes that the pattern is not found in the subject. So it says this pattern is false. And then here it checks if the length of the pattern is well within the length of the subject. And then it says, now let's look at the first character of the pattern, which is at index 0, along with wherever I am in the subject, which is given by this index I sub. If they match, if this return statement gives true, then you say I may have found a pattern beginning at this index. So you set that to be the return index. And then you say I have found a pattern, set it to true. Then you enter a for loop where you continuously walk down the pattern and check if every character in the pattern that you encounter in sequence matches the subject from the index in the same sequence. If there is a mismatch at any point in time, then you reset the return index to not found. Say pattern is not found, come out of the for loop. But if you successfully finish executing this for loop, then you increment the subject and then you can return this value of the index where the pattern was found in the subject, right? So now our first goal is to draw the control flow graph corresponding to this program, right? So as I told you, for control flow graph, this program is spread across these 3 slides, but I'm ignoring this part of the code and this part of the code which is just commented out. I begin to draw control flow graph mainly from here, from this main pattern index method. So if you see this pattern index method, it has a whole series of assignment statements. It has a loop, a branch, another loop, another branch. So here is how the control flow graph of that main method looks like. This node 1 is a dummy node which represents this statement. It says subject and pattern are passed to this node, right? There's no concrete statement representing this, so I have left it blank. Node 2 stands for all these initializations that you do in the beginning of the program, right? All these statements, these 6 statements that are there. if you could put it in different nodes, but typically when we draw control flow graph, when we have a sequence of assignment statements without any control statement in between, just assignment statements one after the other, it's a standard practice to collapse them all into one node and put it as one node, and then augment that node with all these statements. That's what I've done. Because there's not much point in calling each of them a separate node. We really don't find any use for it when it comes to testing. So we collapse it all and put it into one node. So this single node represents all these assignment statements. After that, what do we do in the code? We get into this while loop, right? So that's this while loop at node 3. I say this is the condition that I check in the while loop. You can see that's the condition that I check, right? This condition could be true, this condition could be false. Just for increasing the readability, I have written it only as a label for this node. The reverse of this condition, the negation of this predicate, is true here. I have not mentioned it because the the figure was becoming too cluttered. So I have just left it at that, right? So read the label of this edge as negation of this, right? So I'm entering my while loop here. As per the code, the next is an if statement which checks for another condition. So that I'm entering my if statement here. If statement returns true, this is if statement returning false. After my if statement returns true, I do two assignments. I set, what does it mean for the if statement to return true? I have found the first match. First character of the pattern has found a match in the subject. So I do these two assignments, if you remember, right? I set the index and say I have found the first match by setting the flag to be true. So that's this node 5. After that, after that I enter this for loop. That's this. This is the statement corresponding to the for loop being true. I'm inside the loop. I keep checking if the pattern index matches the subject index. At node 9, I increment the pattern index, go back and repeat this for loop here from 6 to 9. And when the condition fails, I come out of the for loop, right? I break out of the for loop and I'm here. That's what this represents. And then this is the thing that I use to go back for the main while loop. This is when I exit the main while loop, I do this final statement, which is return index. Is it clear? I'm sorry, I had to go back and forth across the slides because there's no way I could have put the whole program and the control flow graph into one slide. So just to summarize, we had looked at a pattern matching program that I had presented to you across 3 slides, which were this, and this. It's a program that has rich control flow structure, looks if pattern given as a string comes as a substring of a subject. What we did here was to take the main method in the program and draw its control flow graph. So I'll repeat this exercise of how control flow graph will look like for various program constructs, but hopefully this example will help you to understand it also. Now we go back to the main goal of this lecture, which is to understand data, right? Data definition and data use. What is data for this particular program? Data is all these variables: not found, I sub, return index, subject, pattern, ispat. So many variables are there, right? So what do? I take the same control flow graph. Instead of annotating it with statements, I say which are the variables that are defined and which are the variables that are used at various nodes in the graph and various edges in the graph. So that's this graph that I have drawn here. It's the same control flow graph. Instead of depicting statements, it now depicts definitions and uses. So if you look at node number 1, it says the definition of 1, that is at node number 1, which are the two variables that are defined. The two variables that are defined at 1 are subject and pattern. You might wonder, this here it is blank, and why have I suddenly put def of 1 as subject and pattern? As I told you when I explained the CFG, read this node 1 as these two patterns, subject and pattern, being passed on as parameters to this method, right? Because it's passed as parameters, I have not depicted here, but because it is passed as parameters, it is defined here. Now, what is the def of 2? If you see, there are so many assignment statements here. It says not found is -1, I sub is 0, return index is not found, ispat is false, and so on, right? So I say definition of two is all the variables that have been initialized here, which is not found, I sub, return index, ispat, subject length, pattern length, right? Now, two also has two uses, which is subject and pattern. Why is it use of subject and pattern? I use the variable subject and pattern that was passed as parameters at node 1 and compute their length here, subject length and pattern length, and assign it to subject length and pattern length. So I have used these two variables, subject length and pattern length. So that's why I have put use of two as subject and pattern, right? There's one more subtle point. Don't worry about it if you don't understand it. If you see, I have initialized not found to be -1. So I have put def of 2 as not found. And I have also initialized return index to be not found, right? So strictly speaking, I should put use of 2 as not found. So you could go ahead and do that, but at a little later we'll see that we typically don't consider what are called local uses of a variable, because I have collapsed all these 5 6 assignment statements into one node in the control flow graph. I say this variable is defined and used within one node, so it's like a local use of a variable. We typically don't capture local uses of variables, but if you're not comfortable with this, if you want to say use of two is subject, pattern, and not found, you can go ahead and do it. There is no harm in that, right? Like this, and move on. Now, I can define defs and uses for edges also. Remember, we saw definition and uses for vertices and definition and uses for edges. So, which is this if a predicate that labels this edge? So, it uses this variables I sub, pattern length, subject length, and ispat. So, that's what I have written here. The use of this edge is this predicate I is this set I sub, pattern length, subject length, ispat. If you remember, I told you that this corresponds to a branch. This is the branch where I enter the while loop, so this predicate is true. This is the branch where I exit the while loop, where the predicate becomes false. Just for readability, I didn't write the condition here. But the same set of variables with this condition negated comes here also. So I say use of this edge 311 and this edge 34 is the same set, right? Because both the predicates, one the positive version and one the negated version, both will use the same set of variables. Similarly, this is the if statement. So use of this edge 410 and this edge 45 is the set subject I sub pattern. And then at statement 5, I have these two assignment statements. So I say return index, ispat, and ipat are defined at the statement. Please note that ipat is defined once here also. Sorry, ispat is defined once here also at 2, and it is defined at 5. So if you go back and look at the code, it is initialized at 2 and its value is reset to another value at 5. So both we call them as definitions because it's again rewritten in memory, right? So definition of node 5 is this set. Similarly, use of node 5 is this isub. Is it clear? So if I move on like this, use of this edge 610 and this edge 67 are all the variables that come in the predicate corresponding to the for loop. Use of this edge 78 and the edge 79 are all the predicates that come in the if loop. And then what do I do at 9? At 9, I do this. I increment the index of searching in the pattern by doing ipat plus plus. So what is ipat plus plus? That reads as ipat is equal to ipat plus 1. So if I read it that way, I am using ipat both in the left hand side and in the right hand side. So it is both defined and used at variable 9. So that's where def of 9 is the same as use of 9, and that is the singleton set ipat, right? I go on like this, finish, right? So what do I do? Just to recap, we have a program like this. We define the control flow graph corresponding to the program. From the control flow graph, I can take the basic control flow structure and instead of augmenting with statements, I augment it with defs and uses of all the variables, right? So is it clear how to do it? So before we move on, I'll go back to the slide where we define defs and uses. So what is a def? Is a place where a value of the variable is stored into memory. What is a use? A place where value of the variable is accessed from memory. Right? Typically, we take a graph, and for every node in the graph, we call what is def of n, and for every edge in the graph, we say what is use of n, and for every edge in the graph, we say what is use of e and def of e. So this, I think I explained this slide already. What I said was at node 1, parameters subject and pattern are forwarded parameters, so they're considered to be explicitly defined at node 1. And I also explained how these uses occur in decision statements. That's what this line item says. And node 9 has a statement which is like ispat plus plus. Suppose I read it as ipat plus plus is ipat plus 1, then it can be thought of as both defining and using this variable, right? So that's why I write def of 9 is the same as use of 9 is the same as ipat. Right. Before we move on, traditionally in literature, there is a paper by Vayukar and her student by name Sarah, which is well quoted for data flow graphs. They distinguish between two different kinds of uses. So they say when a use occurs as a part of an assignment statement or an output statement, that is what is called a computation use or a C use, and a use could occur as a part of a condition statement, right? Like we saw here, this use is a part of a definition at node 2, whereas this use at this edge is a part of a predicate or a condition that occurs as a part of the if statement. So they distinguish between these two uses. One is a computation use, a use that occurs as a part of a printf or as an assignment statement is what is called a computation use. A use that occurs as a part of a decision statement is what is called a predicate use. So instead of talking about DU pairs, definition use pairs, they talk about definition computation use, DCU pairs, or definition predicate use, DPU pairs. So when I talk about a definition computation use DCU pair, I say a variable v is defined at Li and is being subject to computation use at Lj. That is, it's used as a part of an assignment statement or as a printf statement at Lj. When I talk about DPU, I say the variable v is defined at statement Li. It's used in the predicate Lj. In LT says that this predicate at location Lj has evaluated to true. And here LF says the predicate at location J has evaluated to false, right? So when I use it as a part of a predicate, which could be as a part of an if statement or a while statement, the single purpose of that use is to make the predicate evaluate to true or evaluate to false. So, and based on whether it evaluates to true or false, the paths that it takes in the control flow graph could be different. So these two paths are distinguished. This is just for your information. For our purposes of these lectures and this course, we will not distinguish between computation use and predicate use. We will just say all of them are uses. That's what I have done in this control flow graph, right? If you have to be strictly correct, you could call this as predicate use, you could call this as computation use, but for the purposes of this course and this lecture, everything would just be use. What will be the concerns about definitions and uses? As I told you in the beginning of this lecture, a definition may or may not reach a particular use. Why will it not reach a particular use? It could have happened that a variable was defined at a particular location and used at some other location Lj, and then there was no path from Li to Lj. Lj could be a part of a dead code in the program. Or it could be the case that the value was defined and before it was used, it was defined again. It was initialized and before it was put to use again, maybe it was defined by some other statement once again, right? So such things can happen. So we talk about several kinds of paths in the control flow graph. So we say a path from a location Li to another location Lj is def clear with respect to a variable v if v is not given any other value on any of the nodes or edges in the path. So I take a control flow graph augmented with definitions and uses, take a location Li, take another location Lj. V is defined at Li. a variable v is defined at Li. Now there is a path from Li all the way to Lj, which could be another node or an edge. I walk along the path. In between in the path, if the variable v is not defined once again, then you say such a path is def clear, right? If there is a def clear path from Li to Lj with reference to a variable v, we say that the definition of v at Li reaches the use at Lj, right? As I told you, whenever we talk about definitions and use, there's always implicitly a parameter of a variable that is involved, right? So now we talk about what is called a def use path or a du path. What is a du path? A du path with respect to a variable v is a simple path that is def clear from a definition of v to a use of v, right? So what it says in simple terms is that take a node or an edge where a variable is defined. In our case, it will be a node where a variable is defined. Keep going down and take its first use, right? In between, assume that the variable is not defined, and the only other condition that we insist is that the path be simple. There are no cycles in this path. If such is the case, then we say that I have found a path from a definition of a variable to a use of a variable, and I abbreviate it and call it as a du path, right? So du paths have to be simple paths, and they have to go from a definition to a use. In between, there could be intervening uses but no definitions, right? So here is a notation for that. You say DUNINJV means it's a set of all definition use path from location NI to location NJ for the variable V. What is DUNIV? It's a set of all DU paths that start at NI for a variable V, right? If we go back and trace out what are the DU paths. So if you see, there's a small DU path here. There is a definition of subject here, and then there is a use of subject here. So you can say that there is a definition use path for the variable subject. So there's a DU path. Similarly, the term subject is defined here, and look at other nodes where it is used. Like for example, if you see, it is used in this edge 410 and 45. It comes as use of 410 and 45, and in between it's not defined again, right? So this path from 1, 2, 3, 4 to the edge 4, 5 or to the edge 410 is a du path for the variable subject. So hopefully it is clear what I'm saying. There is a du path for the variable subject from the node 1 to the edges 4, 5, 4, 10. Similarly, if you go back, there is a du path for the variable subject from the node 1 to 7, 9 and 7, 8, because it is being used here also but not defined anywhere in between. Please remember, a du path is a path between a definition and a use such that there are no definitions in between in the path of that variable. There could be uses in the path of that variable, that's all right. Like for example, if I take the du path from node 1 to the edges 7, 8 or 7, 9, there is a use of the variable subject in between. We allow that. But we say in between a du path in intermediate nodes or edges, there should not be another definition. A du path with respect to a variable v is a simple path that is def clear from definition to a use, but there could be intervening uses on the path. So another example of a du path for that pattern matching thing is this ipat++, which was, if you remember, at node number 9. If I read ipat++ as this statement, then I can interpret it as the use occurring before the def, because this right hand side needs to be executed before the left hand side. So with that interpretation, I can say that there is a def clear path that goes from node 5 to node 9 for the variable ipat. So that's all I had to tell you for today's lecture. What we did today, just to summarize, is assuming that we have a model of a software artifact, typically a code, as a graph, which means as a control flow graph. How do I actually look at the variables that come in the code and decorate the control flow graph with the definitions and uses of a variable? So once I do, I understand when a variable is defined and when a variable is used. It could be defined and used at nodes. It is typically used only at edges, not defined at edges. Then I talk about a du path or a def clear path and so on. What we will do in the next lecture is to see how these DU paths can be used to define various coverage criteria that will help us to understand when a variable is defined, is it being used? Is it being not used, and so on and so forth. So we'll look at data flow coverage criteria based on definitions and uses in the next lecture. Thank you.